Hello everyone, this is part 3 for the Kinetics videos that I've been producing for you. In this part we're going to be talking about the collision model, and we're going to end out with the Arrhenius equation and activation energy. So to get us started here, we are going to talk about temperature and rate first. So when we look at rates, and we talked about earlier, in the other parts, we really didn't talk about temperature. The temperature itself was basically constant. And now, when you start changing the temperature, what happens? You start to change the rate of the reaction. And a good example for this is something that we've all seen or experienced. Well, I say all. I assume that we've played with glow sticks before. So, one of the experiences I had was when I was younger. I had a glow stick that I wanted to keep around because I was going to go to sleep, and I asked my dad, said, what can I do? He said, put it in the freezer. So I put it in the freezer. Well, what happened was, by putting it in the freezer, I didn't realize it at that time, that the temperature was much colder, obviously being in the freezer. It slowed the rate of reaction down, so when I brought it back out, it was still glowing the next day or so. And so when we talk about temperature, temperature has a dramatic effect on the way and how fast a reaction takes place. You know, if you heat something up, you're going to cause it to react faster. If you cool it down, it's going to cause a slower rate of reaction. That's all hinging on the rate constant we talked about from the rate law. And so, looking at the graph you see here, this is just a very generic graph, but it shows pretty much the same trend that you're going to see. As you increase the temperature, you're going to see an exponential increase in the rate constant for that reaction, and that just depends on what you're looking at. But overall, as the temperature increases, the rate of reaction is going to increase at an exponential level. So this is because rate constant is temperature dependent. Remember that kinetic energy also is tied into temperature, and as you increase the temperature, you're also going to increase the kinetic energy, which ultimately is going to cause the rate of reaction to increase, and that also is going to cause the rate constant to increase. Now, moving into the collision model. So we know that in chemical reactions, we've talked about the fact that bonds are broken and new bonds are formed. So molecules can only react if they collide with each other, and that's the first thing that they have to do, is they have to collide with each other. There are 3 requirements for a reaction to take place. The first one is collision. So molecules colliding together, they must collide with the correct orientation. And orientation is just how they would fit together, like a piece of a puzzle fitting together. And then the third thing is the energy. It needs to have the right amount of energy in order for the reaction to go to completion. So this is a good little diagram here of how a reaction may take place. So here you have the green molecule coming into space where the bigger molecule sits. Now this green molecule is going to collide with the other green molecule. Now, as a result of that, when it makes that collision, it's in the correct orientation at this moment here. And what happens is that this molecule splits in half, and it releases these 2 products that you see here, and still has to follow the same requirements: collision, orientation, and energy. Now, the orientation is really important. If this green molecule had collided on the other side, it would not have reacted. In fact, a lot of gases that you see around, think about the space around you. You have nitrogen gas, you have oxygen gas all around you. They're colliding right now, but that doesn't mean that they're reacting, because it requires a temperature of up to 500 degrees Celsius in order for those molecules to react with each other to form other gases. So just because a molecule collides and it has the right orientation does not necessarily mean that it is going to react, but it still has to meet those 3 requirements. All 3 have to be met at the same point in time. So when we talk about reactants, think about reactions that you've looked at in the past. synthesis, decomposition, single replacement, double replacement. The most reactants you're going to see are 2 reactants. And the reason for the not seeing more than 2 reactants is because you'd have to get, so if you have 3 reactants, you'd have to get all 3 reactants colliding together at the same time with the right orientation and the right amount of energy. That's going to be a very rare incident that would take place. So when you have 1 reactant or 2 reactants, it's much easier and much more likely the odds are in favor for that reaction to take place. So as we talk about energy, we're going to refer to that energy as activation energy. And activation energy is the minimum amount of energy that's needed for a reaction to take place. So it's like going to play putt-putt. Have you ever played putt-putt before? I know I have. This hill is probably the most worst hole. It's probably the most challenging hole. It's the most frustrating hole because what do you have to do? You have to get the ball to the top of the hill. But you have to have just enough energy to get to the top, and then once it gets top, it's going to go on down and do its thing. Sometimes you hit too much energy and it shoots it straight over. We don't want that. And in this case here, what we want is the amount of energy that we see from the top of the hill to where we start at with the reactants. That is representing your activation energy. You want just the right amount of energy so that way you can get over the hill. Once it's over the hill, it's all downhill, and it just does its thing from there on out. Every reaction has some activation energy, but they're not all the same. They're all going to be different because there's different sizes of hills. Some require a lot of energy, some don't require much energy at all. So as we look towards this activation energy, we refer back to what is called the reaction coordinate diagram or the energy diagram. And here you look at this slide here, we see the energy diagram have this basic look to it, so this form. So the activation energy is the energy from the top of the curve to this dashed line. That's the amount of activation energy that you're going to see. Now the energy that's from the dashed line and down to the bottom, so the reactants are found on the left and products are found on the bottom. This is going to represent your delta E or also delta H in terms of your enthalpy. But this is the change of energy. And this delta E oftentimes is represented as being exothermic, endothermic. So this would be an example of an exothermic process because there's a loss of energy in the final products. Now, if I were to look at a endothermic, it would look like this. You'd see where the delta E is found here. And now the activation energy is still from here up to the top of the curve. That does not change. Now, there are a couple points that are also on this graph. So we have the reactants, we have the products, we have your activation energy that's circled here, you have your delta E, and then you have this part that's up on top that's called the activated complex. This is more like an intermediate state. Intermediate states come and go real fast. We'll talk about intermediates more in part 4 of the Kinetics series. So for now, it's just representing at the top of the curve. That's your activated complex. Activated complexes come and go very quickly. So the high point on the diagram also is referred to as a transition state. And why is it called transition state? Because it's transitioning from the reactant to the product. Once it starts down the downhill portion of the curve, it's fast. It goes extremely quickly. So species present in transition state are called the activated complex. The energy gap between the reactants and the activated complex is the activation energy barrier. So as we talk about distribution diagrams, all right, so this is just basically looking at a graph where we study temperature and the effects it has on the amount of energy it takes. We talked about earlier that as you increase the temperature, you're going to increase the rate of reaction. Now in this graph here, the temperature is affecting how many molecules are going to have that requirement to react. and that's the energy requirement that we're talking about. So at higher temperature, you can see there's a larger area under the curve. So that means that there's more molecules that are going to have enough energy to react as long as they meet the other two requirements. At the colder temperature, you see the area in the curve is much less, and that's why the reactions go slower, because there's not enough energy to go around for all the molecules to react at a faster pace. So temperature plays a critical role. This is where the distribution diagram expresses that and illustrates it. All the molecules that are below, that are on to the left of the dashed line, are molecules that do not have enough energy to react. They can collide and they can have the right orientation, but they do not have enough energy, so they will not react with each other. So as a result, the temperature increases, you're going to have an increase in the rate of reaction. Now, I know that this graph is kind of offset, not sure how that happened, but we're going to go with it. So the fraction of molecules can be found through the expression F is equal to E to the negative E sub A divided by RT. E sub A is your activation energy. R is 8.314 joules per mole per Kelvin. Do not forget that. T is your temperature. Always make sure that your temperature is in units of Kelvin here. They have to be consistent with each other, because what's going to happen is when you multiply by R by the temperature, the Kelvin's going to cancel out. And if you have degrees Celsius, you're already throwing off. Another thing you want to make sure you pay attention to is always make sure you know whether you want to work with joules or kilojoules. You can change this joules to kilojoules by dividing by 1,000 if you need to, but in most cases in this particular problem, you're not going to have to worry about doing that. Like I said, always pay attention to the units in the end and what the question's asking for. So Arrhenius equation is a very important equation. It's something that you want to make sure that you write down. It's represented by K, which is rate constant, is equal to A times E to the negative E sub divided by RT. We just saw that in the previous slide. So K, again, rate constant. A is the frequency factor, and you can see it represents the number of collisions of the proper orientation. And what's going to happen here is we're going to do some manipulation with this, and we're going to get it to a form that we can use. So natural log of K is equal to negative E sub A divided by R times 1 over T, where T is temperature, plus the natural log of A. So that is the Arrhenius equation, and is also represented by Y equals mx plus B, where m is equal to negative E sub A divided by R. You can figure out the activation energy by plotting a graph of natural log K versus 1 over T. Remember, temperature is in Kelvin. And so E sub A, we want to solve for that. So what we'll do is we would have E sub A is equal to negative m times R. Now, I will be showing you a problem in just on the next slide or so. We're going to do an example that illustrates the Arrhenius equation and how we go about using it to solve for the activation energy. Okay, so we're going to be looking at an example here. I'm going to show you how we are going to use and can use Excel to solve for the activation energy. Now, I've already worked on a problem here. This is some experimental data that were collected, and we measured the temperature and degrees Celsius, which is this column here, and we measured the rate constant. We calculated rate constant using the rate law. So what I'm going to do is show you how we can go about Excel and use it to our advantage. If you've never used Excel, Excel is a very strong and powerful tool when it comes to doing these calculations and forming the graphs that you need. So let's get started here. Well, first thing I got to do is going back to Arrhenius equation that we just went through. We have this form here where you have natural log of k is equal to negative e sub a divided by r times 1 over t plus the natural log of a. Where there are two things we want. We want the y-axis, we want the x-axis. Y-axis is natural log of k, and x-axis is 1 over the temperature in Kelvin. So what I've done here, that's what I have highlighted here, is I have the 1 over t, and then I have natural log of k. But we need to calculate it. First thing we need to do is convert this into Kelvin. So anytime you want to do a calculation with Excel, you type in the equals. That tells Excel that this is a function that it's getting ready to have to solve for. So we're going to highlight the cell we have here, and then we're going to tell it to add 273. And so once we do that, and you can see that A3 is highlighted because that's the cell I wanted to calculate from, I hit enter, and now we have our temperature in Kelvin. Now we're going to do this for each one of these cells. To make things easier, Excel has it to where you can just automatically calculate it without having to type a bunch of stuff in. So we pull up the crosshairs here. We see that the crosshairs look different when you hold it up, but when you go to the bottom right hand corner of the cell, it turns bold. So I'm going to drag this down, and it populates the next set of calculations for each of those cells. And if I click on this here, you can see that it's calculating from that cell. It's a nice little feature that Excel built in. You can do other things, but that's something we can work on later. For now, I just want to keep it simple. So do the same thing for this column. You type in equals. Since we're doing 1 divided by temperature, we're going to do 1 divided by, and then we're going to highlight the cell that we just calculated, and we're going to hit enter, and we have our 1 divided by temperature. We're going to drag this down, and boom, we have that calculated. We're going to go do the same thing for k. Now we don't have to do any corrections or anything like that. All we got to do is type in and calculate the natural log of k. So we're just going to type in ln, open parentheses. We're going to highlight that, and we're going to close the parentheses, and then hit enter. When you do that, you have your answer. Then we're going to populate that down through the rest of the cells. Okay, so we're at a point now where we have our information that we want to graph. So to do our graph, what we want to do is we have to understand what the x-axis are and then what the y-axis are. So what I'm going to do is I'm going to bring this column down. I'm going to hit Control C here. Let's see if we can do this without changing. Nope. All right. So what I'm going to do here is I'm just going to drag this down to here, and I'm going to do the same thing for this here, but I'm going to pull it next to this, because what I'm doing here is you don't have to do, you can set this up in a way where it's simpler than what I'm doing here, but I want you to understand that your first column is going to be your x-axis and your second column is going to be your y-axis. And you say, well, okay, why do I do it that way? Why is it set up like that? Because you go back to the graph, natural log k is on the y and 1 over t is on the x, and the way Excel does it, first column's x, the second column's y. So now all we need to do is we need to make the graph. So to do this, and this is why I did this, because I want to make it easier, I can highlight those two columns and I can go up, press the insert, find the part where it says charts, and we're going to do a scatter plot. So we're going to pull this up. So here we have our graph. Now the information we see here is all in the graph here. What we need to do now is we need to get the best fit line from the graph so we can figure out the slope. You need a slope to be able to solve for the activation energy. Now, I'm just going to select this cell, the data point here. You can pick any data point that you want. Now I'm going to hold my cursor over it. I'm going to right click that. All right, and when I right click that, I can go down through this table and I can see this add trend line has been populated here. So I want to select that. When I do that, that gives me my best fit line. Since we're working with a linear equation, the y equals mx plus b, make sure you have it selected. It's going to automatically select it, but if it doesn't, make sure you select it here. You can see it's. Now we're going to do I'm going to check the last two boxes at the bottom. And that's how you get your slope from this equation. You get your best fit line. And then you also get the R squared value. R squared value just tells you how good your data is. The closer to 1 you are, the better your data is. In this case, the data is pretty much spot on perfect with a little bit of error in there. So closer to 1, better to get. Now, what we need to do now is we need to figure out slope. Slope is in this equation is negative 18,947. So that's what we get from the linear regression equation there. Now remember, R was 8.314, so we need to know that. So that's part of the calculation. Now, to solve for activation energy, we're going to have to do negative m times R. So basic form here is we're going to set equal to negative. All right, we're going to highlight m, and then we're going to use the asterisk symbol. That's the multiplication symbol, and we're going to multiply by this. And remember, the units for R is joules per mole per Kelvin. The Kelvin's going to go away, and we're going to be left with joules per mole in the end. So now hit enter, and we get a number. So remember, the units for this is joules per mole. We want this to be in kilojoules per mole. It's going to be a little bit easier to work with. So what we're going to do is we're going to take, I press equal, I'm going to divide this by 1,000 so I can get it in kilojoules, because it's 1,000 joules per kilojoule. And so now we have our answer. So this would be representing the activation energy for this particular reaction that we were studying. And it's not a bad thing, 157 kilojoules per mole. That's just how much energy it takes to get over the curve, so that way the reaction will form into the products. So I hope this little demonstration helps you with using Excel. Of course, there are other ways of doing it. You can use your calculators, TI-83, 84, whatever you may have. But Excel itself is a lot easier to use in some ways if you can get comfortable with using it. So if you have any questions, make sure you ask. Thanks. One last thought. The next is part 4 video. It'll be coming up shortly. This video will be going over mechanisms and how we use mechanisms determining the rate law and proving and trying to explain what we see in the experimental results that we calculate and determine. So, see you in the future.